Thank you very much, Frank, for your nice introduction. And before starting my talk, I would like to thank the organizing committee to invite me to give this talk today in front of you. It's a real pleasure to be in Lyon, even if I am French. I know that in Lyon we can eat a lot, good food. And I am afraid that after this week, I will have 2 kilograms more on my balance, so I will not go to the balance after this week of Congress. So today, let's speak not about food, but about biomass a little bit. You will see, I will discuss a little bit on sugar also. But anyway, so today, just to show you, as you know, biomass, and more specifically lignocellulosic biomass, it's a robust compound. So in order to convert this biomass, we need to find some pretreatment and some activation of this biomass. In the literature, you can find a lot of pretreatment, a lot of alternative technology for the conversion of biomass. And among them, we will focus today on 2 types, the dipotectic solvent and the mechanochemistry. So here you have an example on the mechanochemistry, where you have the lignocellulosic biomass that can be fractioned to the 3 main components, lignin, cellulose, and hemicellulose, using ball milling. But if we want to use a catalyst, you have some example on enzyme, for example, but if you want to use a solid catalyst, the main problem using mechanochemistry, it's a solid-solid interaction if you are using cellulose, for instance, because cellulose is not soluble in water, it's not soluble in common organic solvent. So we need to increase this interaction between 2 solids. As you know, if you have 2 stones, for example, you can make the friction of 2 stones. You can have fire, but you cannot do chemistry. So this is the main point here using mechanocatalysis. So to do this, you have some choices, and among them, you have the dipotectic solvent in order to dissolve this biomass compound, or mechanical milling. The mechanical milling will overcome the diffusion barrier in the absence of solvent, and with this mechanical force, you will have a better interaction between the solids and the substrates. How it works? If we look on mechanochemical reaction, this is reaction that will direct absorb the mechanical energy, including impact, compression, shearing, friction, and stretching. And if you look on the literature, you will find some example on the conversion of biomass to fine chemical using mechanocatalysis, for example, the synthesis of sorbitol, glucose, xylose, and so on. And today, I will show you 2 examples of mechanocatalysis. The first one will be on the mechanocatalysis conversion of cellulose to surfactant, and the second one will be the conversion of hemicellulose to oligosaccharides. So let's start with the first example. So we have performed that some years ago with 2 companies, Solvay and HRD company, and the first trial that we have made, it was to perform an impregnation of cellulose with sulfuric acid, 9.8%. We do the dry depolymerization of this cellulose using ball milling. We can see here on the XRD that we have a degrees of the crystallinity index of cellulose, and we obtain some glucans with some degree of polymerization between 6 to 100, and the sulfuric acid was still inside these glucans. So after that, what we have done the glycosylation using N-butanol in order to obtain this surfactant, so alkyl glycoside. And here we can see on this graph, this is the butyl xyloside yield versus the time of the glycosylation reaction. And here, these different curves that you can see, this is the time of ball milling. So here we started from 15 minutes up to 24 hours. And if we can look on 15 minutes, maximum yield of butyl xyloside is around 40%, but after 24 hours of glycosylation reaction. But if we increase the ball milling time to 2 hours, you can see we are in this mass curve here, we are around here, and we can see that after 2 to 3 hours, we can manage to obtain 55% yield of this butyl glucoside. So we have to deal with the time of ball milling in order to activate these glucans in order to perform the glycosylation with N-butanol. But what we wanted to do is a direct glycosylation with enzodecanol. We have done that, no reaction. It was not working. What we have to do is a transglycosylation reaction. So we first do the butyl glucoside, and after you make a reaction with the dodecanol. So this is not what the targeted reaction that we wanted to develop. So after that, what we have done, we have tried several heterogeneous catalysts to do that. So same process. So here we have the cellulose, heterogeneous catalysis, You do the ball milling, you add dodecanol at 150 degrees Celsius, you obtain your surfactant, and after you make the recycling of your solid catalyst. So here in the table, you see a lot of lines, but very easy, a lot of zero, very successful reaction, if you can see. And only one catalyst, the Aquivion, we managed to obtain 70% yield of this alkyl glycoside. And if you look on the structure of Aquivion here, it's a perfluorinated resin with a strong acidity, and it's an amphiphilic properties. So you can make the reaction between dodecanol, a hydrophobic one, and the glucans that were more hydrophilic. So that's why we managed to obtain such yield to the alkyl glycoside using Aquivion. So very interesting catalyst. But for those who know this catalyst, it's expensive catalyst. So if you do not do the recycling of this catalyst, it's not suitable if you want to perform especially surfactants. So here you have the recycling, and before discussing about the recycling, we can see here we have made some optimization of the reaction, and the highest yield that we obtained was 85% with a productivity of 200 kilograms per cubic meter per hour. And for the recycling, we have done 5 runs, no loss in the alkyl glycoside yields. We have done some characterization of the catalyst, so it was quite stable during this reaction. So here, for the ball milling, we have a solid catalyst that was resistant to the mechanical forces, but also to the leaching during the reaction. So that's very important when you are using mechanocatalysis. Second example, based on this process, we decided to apply this technology to the other part of lignocellulosic biomass, meaning hemicellulose. So here we have worked with FCBA, with the Technical Center of Investigation in France. It's located in Grenoble and Bordeaux, in several different places. And we have used a local biomass wastes from our region. The extraction was made by the FCBA. We do the controlled depolymerization here in our lab. And we obtain oligosaccharides. These oligosaccharides can be used as prebiotic fiber, dye-based product, sugar replacement, for instance. And we have done also the amination reaction to this oligosaccharide in order to obtain cosmetics and care products. This last part, I will not present it today. I will just focus on the synthesis of oligosaccharides. So, of course, ball milling. I show you again the different balls. You obtain the powder at the end, the hemicellulose plus the Aquivion. We add water, we obtain the water-soluble oligosaccharide and the dry spent Aquivion that we can make the recycling. During this study, we have fixed different parameters based on our experiences. First, the rotation speed of the ball, the period of milling and the pause. It's very important. I didn't mention it before, but we did 5-minute milling, 5-minute pause. Otherwise, you increase the temperature inside the ball, and you will not have the targeted compound, but you will have some caramelization, some humins, such kind of compound that we do not want. So you need to control the temperature. So we make a pause. We use 3 grams of the catalyst and the hemicellulose, total volume 125 milliliters, and we use 20 balls of zirconia. It's very important, the number of balls, because depending on the number of balls, you will have different results. And also, you can also control the energy demand for this kind of process. What we have make as a parameters that we have studied, Aquivion loading, milling time, hemicellulose wetness. We have performed the analysis of this compound by HPLC size exclusion chromatography, NMR, and mass spectrometry. And the parameters that we want to follow in order to know if the depolymerization was efficient or not, it was the total amount of soluble oligosaccharide, and the targeted compound from this company was oligosaccharide with a degree of polymerization between 3 to 9. So that was the targeted compound that we wanted to obtain. So let's see first the depolymerization of maritime pine hemicellulose. So you take the lignocellulosic biomass, you do an hydrothermal treatment, precipitation in basic media, drying, and you obtain this hemicellulose. This cellulose is soluble in water. We have some cation inside, potassium, sodium, calcium, and magnesium. The hemicellulose is composed of mannan, galactan, glucan, so C6 sugar, and xylan, C5 sugar, and it contains 9.78% of water. If I give you all this information, it's because they are important for the activity and the catalyst recycling and so on after that. So we have done some experiments, always starting for sulfuric acid. This is our reference. So we do the ball milling. You can see that we managed to obtain around 55% of the degree of polymerization between 1 to 9 after 24 hours of milling. And you can see, that between 12 and 24 hours of ball milling, you can see that if you increase the time of ball milling, of course, you will continue the depolymerization process. That's when the blue bar, meaning the degree of polymerization between 3 to 9, will decrease on the benefit of the degree of polymerization for 1 to 2. If we decrease the sulfuric acid amount, nothing. You can see we need a certain amount of acidity in order to perform the depolymerization. And if you increase the amount of sulfuric acid, degradation. So it's not working also. So you have really to control the acidity during the milling. And of course, we benchmark with Aquivion catalyst, and you can see that we have a slightly higher yield to the oligosaccharide with 66%, and we obtain 55% of the targeted compounds. So let's see now some effects, ball milling time and water content using Aquivion. Here's the yield of oligosaccharide soluble in ethanol water. Why ethanol water? This hemicellulose is soluble in water. So if we want to recover and to determine the exact amount of the DP, of the degree of polymerization, of glucans with a DP of polymerization below 14, we need to make a soluble, an extraction of these compounds. That's why we use a mixture of ethanol and water. So here, increasing the time of ball milling, no change. So something that was a little bit surprising for us, why we do not have any increasing of this solubility yield. You can see even the distribution of the product is exactly the same. I will show you after why we have this result. Don't worry, I will answer to this question. And after water content, we decrease the water content, and in that case, we can see that we have an increase of the yield of oligosaccharides. You can see here, we go from 61 to 76. So we need to have a certain amount of water, not too much, but if we continue to decrease the amount of water, it will be not good also. So we have to control the amount of water during this ball milling. But the question was, why during the increase of this ball milling, we have not so an increase of the yield of oligosaccharides? If we look at the Aquivion, remember, perfluorinated sulfonatic resins, we can have an exchange between the cation and the protons present on Aquivion that will deactivate the catalyst. So that's the main problem. So in order to prove this, we have used another hemicellulose sources coming from hardwood kraft pulp. Other extraction methods, we obtain a cellulose that is not soluble in water in that case. We have always some cation present in this hemicellulose, but 4 times lower in quantity than in the previous one. Here, in that case, we have only cis-5 sugar, melanin xylans, and the water content was around 5 weight%. So we know that we need around 3.5 weight% of water. So what we have done, we have decreased the water content, and we have tried the recycling of the Aquivion in that case. And you can see that the Aquivion is quite stable, up to 3 cycles. And if we wash the Aquivion with a diluted chlorhydric acid solution at room temperature, we managed to increase the yield to the xylo oligosaccharide up to 86%. So we need to remove these alkaline earths or alkaline metals present in hemicellulose if we want to recycle this Aquivion. So let's see a little bit about this technology assessment of the ball milling. In the literature, you will see that mechanical milling is often used for the fractionation pre-treatment of lignocellulosic biomass, especially because it reduces the crystallinity of cellulose. There is no inhibitors, no solvents, low environmental risk, but main drawbacks, energy. Okay. So if we look a little bit on the mechanocatalysis, this energy, if we increase the scale up, we can decrease the energy demand. So I think that if we want to work on mechanocatalysis, we have to work on a large scale. And if we compare also the different devices, you will have different energy required depending on the device of of milling that you will use. And here there was a study where you have the energy used for decomposition of cellulose versus the energy applied by ball milling. So in red, this is 7 balls with 400 RPM, and in blue, this is with 600 RPM. This is the rotation speed of the balls. And with different balls. Sorry for French person, between ball and balls, it's not so easy, so I hope you understand what I'm speaking about. And and here you have the simulated results that correlated with the experimental one, and we can see that only 0.005% of the electrical energy input was utilized for the mechanocatalysis. Okay. And what about catalytic conversion of biomass using mechanochemistry? Up to now, I don't know, perhaps in some companies they have developed a large-scale conversion of biomass, but up to now, the TRL is estimated to 2 to 3. So we have to work on that for the scale-up, for the catalytic conversion of biomass using mechanocatalysis. So is it an interesting strategy? I will say yes, definitely. But like from many other strategies, you have some drawbacks. First one, you have to understand the mechanisms that occur during the mechanochemistry, and it's not so easy sometimes. Correlation among data using different devices. For example, if you are doing the same reaction as me with your ball milling, with different conditions and so on, perhaps we will not have the same result as we obtain. So really, we have to focus on that. And the main drawback, catalyst stability and recyclability. We have to have a robust catalyst that will be stable under the mechanical forces, and that's something really we have to work on it, because it's not so easy. The advantage, no solvent, no purification. You can use water-sensitive reactant and catalyst. Reaction time, even if I show you sometimes some 24 hours, but you can do it in a shorter reaction time, and we can scale up the process. So I think that ball milling or mechanocatalysis, it's an interesting approach in order to convert biomass to fine chemicals. So let's move now to the second part of my talk, on the use of deep eutectic solvent for the catalytic conversion of carbohydrate in that part. So here, always the same carbohydrate part. If you want to use carbohydrate, remember, I told you that we have 2 strategies. Or you can use mechanocatalysis, for instance, or you can use a solvent. If you want to use a solvent to do the conversion of carbohydrate, the first one that is coming in your mind, I think it's water. When you dissolve sugar in water, no problem, okay? Organic solvent, not. Ethanol, why not? You can use this solvent. But the main problem of using water, for instance, it's when you have a high concentration feed of carbohydrate inside in water, and you eat the water with sugar, you will obtain a nice caramel, very nice one. That we like it for cake, cooking, and so on, but not for chemistry, even if you have to wash the vessel after your reaction and you have a lot of caramel inside. So that's something we want to avoid. Solution, going at a lower temperature, that could be a solution. But in that case, most often you have quite no conversion, no reaction. So we have to handle with the decomposition and the reaction activity. So the main idea was to use deep eutectic solvents. I don't know if you are aware of these solvents, but I will just give you some slight information on this solvent. So deep eutectic solvent, generally, it's composed of 2 or 3 cheap non-toxic compounds that can form an eutectic mixture by forming hydrogen bonds. So here you have an example when you have choline chloride, solid one, fructose, another solid one. We mix both of them and you obtain a liquid phase. You know, when you have some secondary school students coming to our lab and that we do that, it's like magic for them, because 2 solid becomes liquid and they are very happy, because when you go back to the room temperature, they are still liquid. So if you look on the 4th type of deep eutectic solvents that you can obtain, there are different forms. You have an hydrogen bond donor, hydrogen bond acceptor. You can see some example here of the high deep eutectic solvents that you can obtain. There are many. I didn't want to show you how many combinations you can do. Okay, I just give you general formula. Very simple to prepare. When I say that, I have some comments sometimes to say, I tried to prepare this deep eutectic solvent and it was not so easy. Normally it's simple, okay? So you just have to eat, but you have to choose the right composition between your hydrogen bond donor and your hydrogen bond acceptor. If you have a little bit different from the eutectic point, I mean, you will have some difficulty to obtain your deep eutectic solvent. Normally they are unreactive with water, And you can add water inside a little bit, but not too much, because otherwise you will disrupt these hydrogen bonds, and like this you will have a ternary mixture, but no more a dipotectic solvent. Many of them are biodegradable and normally low cost. You can see in the example that I have chosen here to represent the different class of dipotectic solvent, you can see that in most of them we are using choline chloride. In literature, we say, okay, it's a non-toxic compound, produced at a very large scale and so on, but up to now, the main sources of choline chloride production is from petroleum sources. So we have to be aware about that, just for your information. And I will give you some example on this dipotectic solvent, and I will give you some example on the synthesis of furanic derivatives on the first part, and after I will give you some example on one hydrogenation reaction. And in every example, I will give you advantage and disadvantage of dipotectic solvent. You will see that nothing is very good and nothing is very bad. We have to handle with some average sometimes. So just for a reminder, cellulose can be depolymerized to glucose, glucose can be isomerized to fructose, fructose can be dehydrated to 5-hydroxymethylfurfural, this HMF compound. During this reaction, we have several bottlenecks. It's if you go from glucose or fructose to HMF, it's acid catalyst. The main problem is the stability of HMF because it's not a stable compound, so we have really to pay attention to this. Especially when you have the dehydration reaction, you have the formation of water, and HMF can react with water in order to produce levulinic and formic acid. So we have to play with the nature of the solvent for such kind of reaction. And of course, I'm not speaking about the humins that you can obtain. You will see I will never show you 100% yield, but yesterday there was a very nice talk of Avancium about the humin characterization and formation. Green came, 2024, for all of them who are interested. I made some advertising, very nice paper. So let's see what we have done. So we decided choline chloride and fructose, you can make a dipotectic solvent. And we decided to use as a catalyst betaine hydrochloride with 1.9 pKa that is obtained from sugar beet industry. This is this compound here. It's solid. Choline chloride is solid. So you can imagine if you use choline chloride and fructose, it will be a liquid. But if you add a betaine hydrochloride inside, you will have like a big mass. And the main problem will be the viscosity. You cannot steer. Even with mechanical steering, it will be very difficult. So what we have done, we have used a little bit water inside, because in order to favor the steering during the reaction. And you will see in most of the example, you will see that there is some water inside our solution of dipotectic solvent. So remember, I told you we wanted to use a high concentrated feed of carbohydrate. We have tried with betaine hydrochloride, good yield to HMF. We do I forgot to tell you, during all this reaction, we do the extraction of HMF during the synthesis with methyl-isobutylcation. We managed to obtain 84%, purity 95%. We managed to make the recycling of betaine hydrochloride. But you can see we use only 10 weight% of fructose. If we increase the amount of fructose, the yield was decreasing, and we do not obtain so nice results. So we started with another catalyst. And I call it a catalyst, even if it's carbon dioxide and it's a large excess. We put it with carbon dioxide. We introduce carbon dioxide in the reaction media, so containing fructose and choline chloride, 40 bar of carbon dioxide, 120 degrees. And this sugar and choline chloride has always a little bit water inside. We can manage to form carbonic acid. We managed to obtain 70% yield, but here we can use 100 weight% of fructose. Alors, when I say 100 weight%, it means that we have 1 gram of fructose, 1 gram of choline chloride. This is my 100 weight% in order that you understand. So half in a weight percentage. And the advantage of carbon dioxide. You remove carbon dioxide, you can recover it, and you do your loop. So that was the first attempt that we managed in order to obtain a furanic derivative for a high concentrated feed of fructose. How it works? Why? Why we can do it with carbon dioxide and why we cannot do it with betaine hydrochloride? So we have made some tests, and in fact, what we obtain when we have the formation of HMF, we can have a dipotectic solvent that is formed between HMF and choline chloride. So normally you should be a little bit surprised about that. If you have a dipotectic solvent, why you do not have a dipotectic solvent when you are using betaine hydrochloride? Because the presence of betaine hydrochloride will prevent the formation of this dipotectic solvent. And carbon dioxide will not, sorry, I made them, will not help to, will not be negative for the formation of this dipotectic solvent between choline chloride and HMF. So let's continue. HMF from cellulose. We tried the several strategies. You can see the yield are not so high. We started with microcellulose cellulose. We do the first step using iron chloride catalyst in water. We were using microwave in that case. And after we use a second condition, we added 3% molar of aluminum chloride, 2 grams of choline chloride, and methylisobutyl ketone in order to extract the HMF form. And we obtained 27%. So here, if you look, we were looking at the mechanism. The water that is present here will help to form the species of aluminum hydroxyl compound for the isomerization of glucose to fructose. And by the formation of this species, you have the release of HCl that will help to dehydrated HMF. So when you look at that, you say, no need to use choline chloride. Why we are using choline chloride? You can see the mechanism. There is no impact of choline chloride. And in fact, without choline chloride, the yield is much more lower because choline chloride, we have made some calculation with the Institut Chimique Clermont-Ferrand in France. And we can see that there is a modification of the coordination sphere of the methyl hydroxide species by choline chloride. So we have an effect using choline chloride. And if we combine with ball milling, you do a pretreatment of cellulose. So it means that you decrease the crystallinity of cellulose. We manage to obtain 49% of HMF yield. We continue on that. It was a period when we were working a lot of HMF and what we can do with HMF. And since we managed to produce HMF using choline chloride, we wanted to produce a diformylfuran, which is an oxidated compound. And if we look at this reaction, we did an acid here, and after an oxidative catalyst. So we decided the very well-known catalyst, which is molybdenum vanadium containing kegging heteropolyl acid catalyst that were used during this reaction. In the literature, at this moment, the main solvent that was used for this reaction was dimethyl sulfoxide. You can imagine that we want to avoid dimethyl sulfoxide. So what we have performed, we try to do in 100% choline chloride. You imagine, we say, oh yes, we will obtain HMF and so on, but the main problem is that after oxidation, what we obtain, a solid. So we stop at 40% yield, and nothing has occurred after with choline chloride. So we decided to use other co-solvents. Of course, we have tried many of them, and you can see that the best one was always with adding a little bit DMSO inside. So we obtained higher yield with 65% choline chloride and 35% DMSO in weight. What was the role of choline chloride? Helps the in situ formation of HMF by stabilizing effect, as I showed you before, but it helps also to solubilize oxygen. The role of DMSO, many assumptions, and we can discuss on this later on, but up to now I have many hypotheses, but not one that was proved by control experiments. So I will not discuss so much today on the effect of dimethyl sulfoxide. So 2 last examples, and I will finish with the xylose part, because we were with C6 sugar, and now we will go to C5 sugar. So hemicellulose, xylose, you do the dehydration always in presence of an acid to furfural, and always the same idea to use a high concentrated feed of xylose. So we have done that. You can see here that we were not using an heterogeneous catalyst. We were using only HCl, because the main purpose here was to know exactly, the effect of the solvents. So choline chloride, you can see that the xylose content was between 33 to 58%, quite high. And here on this graph, you have the conversion in blue with neat water, in black choline chloride and water, a little bit with water in order to avoid the viscosity issue. And in green, you have sodium chloride with water, because sodium chloride is known in the literature to have a salt-out effect in order to increase the extraction of HMF by methylisobutyl ketone. If you look at that, the tendency, for me, when I look at the conversion, you can say it's almost similar with the experimental issue analysis and so on. There are not so much effect. But if we look on the furfural yield, you can see that the choline chloride with water, the black line, we obtain a furfural yield of around 70%. starting from a high concentrated feed of xylose. And it's much more higher than water on a sodium chloride, water issue. But the question is, it's not a salt-out effect. How it can work? Really, I mean, that was our question. So we decided to follow the reaction by NMR, proton NMR and carbon NMR. So we started the reaction at T0 until 1 hour. And you can see here, I make in a red cycle here, you have the formation of a byproduct. So we were thinking about what it can be, this byproduct. We have done some counter experiment. We have synthesized this byproduct, and I will give you the results. This is a choline xyloside that is formed. So in that case, we have choline chloride that is reacting with xylose. And by this reaction, you avoid the degradation of the sugar, and after you can manage to obtain furfural. So about the mechanism, how it works. So you have the formation of this choline xyloside. After you have the 2OH protonation here. So you have the release of water, you have a ring contraction, and after you have the double dehydration in order to produce furfural. Remember, I told you that from fructose, we have a bipotectic solvent between choline chloride and HMF. Why it is different here? Simply, we have performed some experiment because when we saw this result, we say perhaps we have missed something some years ago because it can happen. And if we want to produce fructose, I mean, we start from fructose and we want to produce this choline fructosyl, we never managed to do it. It's impossible to do it. You can do this choline xylosyl, you can do the reaction between choline chloride and xylose, choline chloride and glucose, but never between choline chloride and fructose. If you manage to do it, really call me. I'm very interested in because we have tried many experiments and it was quite impossible. So it's not the same mechanism. So you can see the difficulty with the same strategy, with different sugar, we do not have the same mechanism. And the last example will be on the hydrogenation of xylose to xylitol. So here you have always a xylose formation, hydrogenation. Why we wanted to study this reaction? Because you know that xylitol is one of the most popular natural sweeteners. We can use it a lot, and there are a lot of production of this compound, and it's very interesting. You can use many hydrogenated catalysts. And here it was the same idea. We wanted to use dipotectic solvent for this conversion. So we decided to use a nickel iron catalyst. So here you have the preparation method. So we started with chlorine nickel, iron sulfate, with sodium hydroxide, ethylene glycol, hydrazine hydrate, heating for 120 degrees Celsius for 16 hours, and we obtained these nanoparticles of nickel iron. We have still studied different ratio between nickel and iron, and the best one was nickel 3 and iron 1, so I will show you only the result with nickel 3 and iron 1 for this reaction. So here you have the first reaction using this dipotectic solvent. I will explain you this graph. So here you have the performance. In orange, this is xylitol yield. In blue, conversion. And here you have the ratio, in molar ratio, between xylose and choline chloride. So here more you go to this part, you have an increase of the xylose content inside the solution. So it means this is what we want. We want to work on this ratio because we have a high concentrated feed of sugar. But unfortunately, as you can see, more you increase the concentration of xylose inside your xylose choline chloride mixture, you have a degrees of the yield and degrees of the conversion. But we wanted, when we want to do something, we try different experiments and we try to optimize the reactant. So we have selected this 3:1 molar ratio, so xylose to choline chloride. We have studied the catalyst compound. And we can see that if we increase the catalyst compound, so here, for your information, it's 8.9 weight%, and it's around 100 milligrams of catalyst, and the mixture xylose choline chloride is 1 gram almost. So it's just for you just to have an idea about the quantity. And we can see that we have an increase of xylitol yield and an increase also of the conversion. So it means that we managed to obtain a good conversion with a high concentrated feed. So we were very happy about that. But next, you will see the disappointed part of this work. We try to do the recycling. And I will not comment this graph. This is a different cycle. up to 3, you can see there is a sharp decrease of the xylitol yield and xylose conversion. But the solution was quite clear. No degradation, because that's something that we were thinking about. What has happened? We have made some characterization of the catalyst, not so much change on the nickel iron particles and so on. So that was not the case. So we have done thermogravimetry analysis. So here you have in blue the fresh catalyst. Here after the reaction. And here it's just a comparison if you use water instead of dipotectic solvent. So you can see that with water you have no difference between the fresh one, but with dipotectic solvent you have quite a big difference on thermal analysis. So we were thinking that some products were adsorbed on the catalyst surface and so on, so we tried to wash the catalyst. So we wash it by water, no change, by ethyl acetate, and in that case you can see that we managed to have exactly the same profile in thermogravimetry. So we say, okay, yes, successful. Now we will try the catalyst. And unfortunately, no, the reactivity was not so high. So in that case, we have some compounds that are adsorbed on the catalyst surface that will stick on it, even with washing, that will not move, that are very stable, and that will prevent the reactivity. So you can see, I show you some success story with dipotectic solvent and some others that are not fully successful, but it's normal. I think that's research, and I think that we have to show also the results that are not wonderful, that you will not say wow. And I'm always dreaming about, this journal of unsuccessful chemistry in order to avoid to do some experiments that we are sure that it will not work. Anyway, just to summarize the use of dipotectic solvents, the main advantage I think that depending on the different reactions that you want to do, you can use dipotectic solvent, but do not say that it will be the wonderful solvent and so on. You are really to think about which type of reaction you want to do. The advantage of this dipotectic solvent, the easy preparation, that makes them cheaper than ionic liquid, and most of the components are available. Are available. Disadvantage, viscosity, and we lack a fundamental knowledge about the formation of dipotectic solvents. So just to show you what we have to see, the recyclability, influence of water, if this solvent can be used in biorefinery, and can we produce them on the large scale. I would like to finish, so with all the person working on that part, special thanks to François Jérôme. I think he's in the room, I hope, otherwise I will not speak with him anymore. That is my collaborator since, 2009, so we have made a lot of things together in work. And all the company, FCBA, Solvay, ARD, and of course, the Région Nouvelle-Aquitaine for the funding, ANR also, because we have 2 projects funded by ANR. And just to show you, because I know that there are many French people, but for the other, here is our city and the nice place. We do not eat perhaps so well, but we eat a lot also in Poitiers, so you can come when you want. And thank you very much for your kind attention.